Hello, my name is East Village and welcome to episode 3 of this JavaBot tutorial. Last time I said we were going to look at the data packet, and so we are, but we won't do as much refactoring as previously planned. I figured we want to get to the juicy stuff as fast as possible, and the juicy stuff is a state machine, and I'll explain more when we get there. We still have to talk a bit about the data packet. Why do we even have a data packet? Why don't we just use the GameTick packet we get directly from the game? And well, there are 3 good reasons. First off, we get to decide the layout of this data packet, and we can choose the structure that is most optimal for our bot. Secondly, we can also put new values in there. Imagine you have some big calculation that you only want to do once. Well, you can take the result of that one, put it into the data packet, and now it's available everywhere. And third, there's this really good reason as Taha expresses it right here. We should always translate to our own data structure immediately. And what he means is that the GameTick packet can change. It doesn't happen that often anymore, but technically it can still change, and that change might be a breaking change. So if you're using something from the GameTick packet and it's now different, then you have to go and fix it everywhere in your code. But if you have your own data structure, then the only place you need to fix it is in that data structure, and that's why we have the data packet. With that out of the way, we're going to take a quick look at the data packet and its content. And the reason why is, as I have mentioned previously, sometimes the example bots change, so we're going to make sure that you have the same values as I have, so we can make the state machine later. There are also a few changes that we're going to make. First off, I just want to put this controls output into the input, so it's not alone, and we can just refactor it. Again, IntelliJ is very smart and it can do it for you. So now we can delete the output packet, and of course this is now not only input, it is also output, so let's rename it, which we can do here. Let's call it data. Wait, why? Okay, ironically enough, I just said that IntelliJ was super smart, but it turns out that it didn't update these fields, which I actually expected it to do. I don't know. I'm pretty sure it used to do that. So we're just going to update all of these manually. That's not a big problem. And we might have some imports that are broken as well. Oh no. Yeah, that should be it. That's the first time IntelliJ doesn't behave. Nope, it turns out there are more places we need to fix. Dang it, IntelliJ. So I tried to compile and it gave me these errors. I'm just checking, make sure that all of them are here. So now we are back in the DataPack. And as it says here, we can edit this class as much as we want. And the same thing goes for all of the other things right here. So now I'm just gonna scroll through this and show you what we got in here. There's the car, which is our own car. Then there's a list of all cars, and this is also including ourselves, we have to remember that. Then there's the ball, and our team, and our index. So what is a car? Well, about the car we have a position, velocity, orientation, boost, whether we have wheel contact, so if we're touching the ground or not. We can also see if we're supersonic, which team this particular car is on, and this elapsed seconds is actually just how far into the game did we get this car data. It's not super important, don't worry about it. For the ball we have something similar, position, velocity and spin. We are mostly interested in the position and velocity most of the time, because spin only has a very small effect. But in the future we could add other values like where is this ball going to land next time, and is it going towards the goal. We might also place those in the data packet. We'll see. Then as the car orientation, we have seen this in the previous episode. So we have a forward, up and left to describe how a thing is rotated in space. And those are the only fields in here. The controls output of course has the steer, pitch, yaw, roll, throttle, and a jump, boost, slide and use item button. And these basically just map to the buttons on your controller. And we send one of these back every time the frameworks ask us, but what are we doing? We say we are pressing these buttons, or we are pressing these buttons. Again, your data packet might look a bit different, but if we have these values, we're good. Now there's a few things we want to add. We want to have a reference to our own bud in here. And the reason why is because the goblin bud, or whatever your bud is called, is going to hold the state of a bud. So I'll just add a field here. And we of course need to add this to the constructor. Now we don't actually need the player index because we can get the index from the bud. Like this. And of course we also have to remember to save the bud. So back in the goblin we have to pass it the goblin itself. That's down here in the other process input function. And we simply pass ourself and no index. We can also just get rid of this warning here because it says here this is redundant, and I agree. Let's just do it in one go and process the input. Oh, and I just noticed here that it still says sample bud, so let's just say goblin instead, goblin number, whatever index we are. And now we are at it. Let's just remove this function we had up here, the drop debug lines. It was a function we used to display whether we were going left or right in the example, but we'll be doing something similar in the future, but right now we don't need this function. So let's delete it. And now I believe we are ready to talk about state machines. State machines are probably the simplest kind of AI there is. It consists of some states and then transitions between them, and those transitions happen once some condition is fulfilled. In one way we could say that we already have a state machine, we just only have one state, and that is the AtbaState that chases the ball. But we are going to add more states. So what we're going to add is another state with some boost collection. And then we're going to say that when we have run out of boost, we'll go for boost instead. And once we have boost again, we'll switch back to our AtbaState and chase the ball. And once we have that working, we can easily expand it and add more states. Like go back and defend, make an aerial, get in position, all sorts of things. But we'll start out with this AtbaState behavior and simple boost collection. So first let's make a packet for a state. And we're going to make a state class that is going to be a base class for all the states. It's going to be abstract so we can derive from it. In the state class we're going to have one method, for now at least, and that's the execute method. It takes our data packet as an argument, so it has all our data, and it returns a controls output with the things we want to do. And then of course it's abstract because each state is going to implement their own behavior in this function. The two states we discussed is actually kind of similar, Both of them are about going to a single specific point. So we could actually make a general move to a point state, and we're going to do that. And this one, of course, extends our state. And it has to override our execute function. So let's go back to our goblin, our main bug. And we can actually just copy paste this. This is basically what it's going to do. And we're just going to replace these with data now. So again, we get the ball position, we get our car and the car's position, and then we use this dot product trick to find which way we are going to steer. But now, since we want to move to any kind of point, there's a few parameters. Like, maybe it's not the ball we are moving towards. This position could be something else, like a boost pad. We may also think about the speed. Like, maybe we don't want to go full throttle all the time. Or maybe we want to boost and go even faster. So we're going to add those parameters. And we're just going to add them out here in the field. So there's the target we're going towards. By default, we'll just go towards the center. We expect that any kind of state would set this for us. And then there's the target speed, about how fast do we want to go. Now let's use these arguments. So the target we're going towards is pretty easy. We're just going to replace this ball position now. Instead of having a ball position, we'll use the target. For the speed though, it's going to be a bit harder. We're going to use some math again. We're going to check our current speed. Are we going too fast or are we going too slow? And based on that, we'll find our throttle. So let's start by finding our current speed. And let's find our current speed towards the target. So that means we might be going in a completely different direction, but we want to know how much of that is in the correct direction. And once again, we'll use the dot product. So if I remember correctly, this is our car's velocity dotted with the difference between the car and the ball normalized. So this is a vector towards the ball, and it's only 1 unit long, which means when we dot it with the velocity, the result should be the amount that a velocity is in the same direction as the car to ball. And that is our current speed. So if we are going straight towards this target, our current speed should be equal to the magnitude of the velocity. And yeah, this is not a car to ball anymore. It's car to target. And now we want to compare it with the target speed. So if our current speed is less than our target speed, we need to go faster. So we will set our throttle to 1. We'll just have to make a throttle variable. But in case we are going too fast, we need to slow down, but not too much, of course. In Rocket League, braking is much stronger than throttling, so we may not want to just go with 0. Let's calculate how much faster we are going than what we are supposed to. And we want to brake faster the bigger this number is. So we could say 0.5 minus our extra speed divided by some number so it doesn't get too fast. Remember, extra speed is 500 or something. So if we divide by 500, we'll get about 1. And in that case, we will do a sort of hard break. Maybe 500 is actually not enough. We'll test that. Actually, I think this 0.5 might be too much. Let's try 0.3. Please remember that the throttle can't be lower than -1. Luckily, our control's output has a clamp function in here, which will clamp it to between +1 and -1, so it'll always be in the correct range. Which means we don't have to worry about this number being too negative. We can just pass it along as it is. And we'll put this down here in the controller, of course. We can also consider boosting. The reason I chose 1410 as the standard up here is because that's the approximate speed that you can reach with just throttling. But if the target speed is higher than this, we'll need to boost. So we can add some code for that as well. That'll be right here as well. And similarly, we add the boost down here. Boost is really effective about increasing your speed, but I know from experience that boost actually takes a few frames to toggle off. So for that reason we might want to add a small buffer so we don't overshoot our target speed and have to brake. And by a buffer I mean something like this. So our current speed plus 60. If that is still not greater than the target speed, then we'll boost. But if the difference is less than 60, then we won't boost. Then we'll just turn it off, and then those few frames later, the actual boost is away and we're no longer accelerating. And hopefully we'll hit the correct speed. Okay, so that's our general move to point state. Now let's move towards some specific points in some specific scenarios. We'll start with the AtbaState behavior. So that'll be an AtbaState. The AtbaState, of course, extends the move to point state. And it should also have this execute function. And we will call the super because that's where we place all our logic, all the move to point behavior here. But before we call it, we're going to set those parameters from before. So for instance, our target will be the ball position, and let's set our target speed to something like 1800. So we will see the bot boost now. And that also means we might run out of boost, which is a great reason to make a boost collection state. This is going to be very similar. Again, we have a target and a target speed. For a target, we want to find a position of a big boost pad, preferably the nearest one. And for the speed, I was thinking, well, if we're going to pick up a big boost pad in just a second anyway, let's just use our remaining boost to get there as fast as possible. 2300 is the max speed you can reach as the car. But now how do we find the closest boost pad? Well, let's look in the DataPacket. And you'll see here that we actually don't have any boost pads in here. And that's because this Java example has a special manager just for the boost pads. It's right up here. So there's the boost pad, which is every instance of a boost pad on the field, and we have the boost manager, which takes care of updating and maintaining all the boosts. You can also see that being updated if we look in our bot, and you'll see down here in this process input function that the boost manager is called with the load game tick packet, and it will update the boost pads with the relevant data here. So it's kind of like a separate data packet just for the boosts. And that's kind of okay. In the boost manager there are 3 different arrays. One with all the boost, one with only the full boost, or the big boost pads, and then all the small boost pads. And you can see they're put into the different array lists down here. And we can get all the full boost pads right here by calling this function. And since we're only interested in the big pads, let's just use that one. But we want to get the closest one, so we're going to have to calculate which one is closest. This would be a great thing to put in the data packet. So we will add the value closest full boost. And we'll calculate this each time, so we only have to do it once, even though we might use this value multiple places in our code. It would be useful for some strategic decision, for instance. To find the closest full boost, we're going to have to measure the distance to each one and find the one that has the lowest distance. So while we iterate through the boost pads, we'll just store the closest one in a variable. And we also need to record what was the shortest distance so far. And now we can start iterating through the boost pads. To calculate the distance, we simply do and we have to do pad.getLocation right now, and that's because of the way that the boost pads are implemented. They have a getter instead of just making this one public. And I will probably make this one public and also rename it to position off stream at some point, because there's no reason not to. Okay, now we know the distance to this pad. Let's check if it was closer than the closest one we found so far. If that is true, then we found a new closest pad. And we also have to save the shortest distance to make sure that it's ready for next iteration. So now we should know the closest pad, and we can also save the distance actually. That might also be useful. Great, now we have this for all future. Now let's go back to the boost collection state. And our target is now simply the closest boost pad. Of course, the closest one might not always be the most optimal. It might also have been picked up and not active. And that's actually easy to check, so let's just do that. It is as simple as just saying, is the pad active? And we'll just put another parenthesis, just to make it clear. And this of course just asks if the pad is active right now. We do not consider if it will become active in the time it takes to reach it. We can actually see the timer in the game tick packet. But that's another thing we can improve about with in the future. And we are actually almost ready. We just need to use these 2 states we have made. We're going to hold our current state in the bot. So right here we'll put a state variable, and we can change this whenever we want to change state. Our default will just be the AtbaState. Of course, right now we are never changing state, but let's just try and see if the AtbaState works. So now our bot is running. Let's start up Rocket League by running this run.py. I actually have Rocket League open already from an earlier test. We should see the match starting. Yes. And remember, the orange bot is still all-star right here. So it's the blue bot we have to look for. Something seems wrong. It's not boosting. Oh yeah, that's right. Of course, we need to call the state's execute function. It's just me being dumb. And for some reason I can't find the execute method. Oh, it's not public. There we go. So now what our bot will do is we'll take our current state and we'll execute that state. Let's try and rerun our bot. We'll get a compile error because these also need to be public. Now we can rerun. And it looks like our bot is using lots of boost, even when going in the wrong direction. Otherwise it seems to be working just fine. Now we just need to make it switch to the CollectBoostState. And we simply add this logic right here in the AtbaState. So let's change to the boost state once we are running out of boost. So I just pick 10 here, so if we have less than 10 boost, we'll start collecting some boost. And that's it. We just have to add some similar logic to the CollectBoostState. So once our bot has some boost again, we will switch back to the AtbaState. Now I just picked 60, but it doesn't really matter because we are going towards a full boost pad. But we may get lucky and pick up a lot of small boost pads on the way, and in that case, let's just switch to the AtbaState as well. Now let's see this in action. Yep, we are definitely going for boost. It seems like we do have a hard time getting down from the walls though. And yeah, here in the kickoff we also we abandoned the kickoff halfway through. That's not good. So it looks like a kickoff state would be really handy to have right now. But other than that, our boost collection works, and we now switches back and forth depending on whether we are missing boost. So we got some boost, going for the ball. Now we're out of boost, and going for some boost. So this looks pretty good. There's a few things, like we are abandoning the kickoff halfway through. I think we'll look at that next time. Then there's also a thing where we get stuck on the wall from time to time. And then we're boosting in the wrong direction. Those are some things we'll look at next time. See ya.